So my talk is about let the terrain do the talking. So it's about looking at the shape of the landform and understanding what that can tell us. And let me get my slides going forward. So a bit of an introduction. I'm using two main bits of software today. The first is a bit of freeware called Stereo Photo Maker, and that allows us to view the retro lens images, historic aerial photos in 3D. And the retro lens, I think the first photos started off in about 2015. And according to their website, they're mostly going to be finished up this year, which is fantastic to have all those old aerial photos. Obviously, viewing stereo photo pairs is nothing new. It's been around for a long time. Here's a picture from someone from 1937. Stereoscopes, in fact, were invented in 1838, so 183 years ago. The first aerial photo was back in 1860 from a hot air balloon, I believe, so that's over 160 years old as well. So something that's been around and used for a long period of time. The other source of information we're using today, we're using QGIS, which is freeware. I think it was first released back in about 2009 and is updated on a regular basis. Free to download and use. Do consider supporting if you're using it lots. And that's combined with the full coverage we have of Northland with LiDAR. It was flown in 2018 and released in 2020, thanks to Northland Regional Council and the Provincial Growth Fund. And that I have on a hard drive that I use on a regular basis. And as Sally mentioned, the presentations to show the various uses. It's not a full software tutorial on how to go about it. First question I say is, why is it important to look at the terrain and analyse the terrain? Well, if you have a friction angle of 30 degrees, things normally stand up pretty well. If you have a friction angle of 10 degrees, things don't normally stand up very well. In Northland, we have lots of soft rocks with lots of shear surfaces and bedding planes, and they affect the terrain in a multitude of ways and cause many problems. They're really hard to find. Looking at the terrain is one of the wonderful, best ways of identifying risks and hazards around that. Another aspect is slope angle and stability don't correlate very well. It's the shape of the landform that tells us more than the slope. And I pulled a little graph here out of a paper. It was actually near Wanganui, where they built up a landslide database, and then they assessed what slopes the landslides were occurring on and what slopes didn't have landslide. And you can see from the peaks here, the landslides on average have flatter slopes than the land without it. So the steeper land is actually more stable. So we need to go a bit beyond just looking at slope angle. Our geology can change pretty quickly. Example in a picture we'll get to later on. So it allows us to identify where changes are occurring, and also it's pretty hard to get representative lab testing from a site like that. Why us? Well, our clients expect us to do a good job. We don't have many excuses when we've got free data and free software available. It's relatively quick and easy to learn once you get some practice. Once you start doing it, you'll get better and better and better. So the intent of this presentation is not state of the art. It's hopefully practical that the average geotech engineer or geologist in Northland can utilise on a day-to-day basis. And a final disclaimer, I'm an engineer, not a geologist. Excuse me in my bits there. I'm not a GIS expert. There may be some watching in, but it's just something I've learned over the last couple of years. And you've got me for the presentation because I volunteered, not because of my selected merit. Any people who have more tips to share with me, let me know. A few people have given me tips along the way to get me going. And there'll be time for some questions in the end, but I'll get into it. The presentation's about an hour. Obviously, you can sneak away at any time, given it's online. So we will get into QGIS. So hopefully that's come through on your screens. There may be bits of lag as we go. So this is Northland with the geological map overlay and a bit of terrain shading behind it. For the first site we're going to look at, we're going to go to Waipu. So I'm just going to, first I'll show what layers I've got. On the left is a list of the layers in this version of QGIS that I've put together. I've got my tile index for the LiDAR. I've got an 8-meter digital elevation model, which allows me to put the terrain behind this geological map in larger areas. I've got some links from Lens, so I haven't downloaded the data, it just links through to their website and gives me the property boundaries, it gives me the property titles, it gives me the ownership information. I've got some links to the GNS website, which is giving me some geological maps, the QMap series, the geology of the Whangarei urban area, and I've scanned in an old 1920s geological map from Kamo as well. I've got some DEMs. So the LiDAR in Northlands, they did selected places from 2007 through to 2018. So I've got the old LiDAR there. And then I've compiled together a selection of projects. And at the bottom, I have various sources of aerial photos, again, that just pulls them through online. So that's what I've got loaded in. And first of all, we're going to head to Waipu. And I'll turn off some other things. So hopefully that's come through and you can see it there. So what we are seeing is the property boundary information from Waipu through from Lens, and we are seeing the digital elevation model files that I've just loaded in directly. So I've just gone and got 2 files. I've found the link and loaded them in, pretty simple, and I've just merged them together, which we can do. There's a little tool at the top. I can just merge 2 files together, which allows me to manipulate them as one. Oh, sorry, it jumped around there. So what I can do with this picture here is I can just play with the settings of these files here, and I can change the render type to a hillshade. I can change my Z factor to put a bit of extra exaggeration on it. The azimuth allows you to change the sun angle and change where the lighting's come from on the terrain shading. And I'm just going to change the settings here so it's a little less pixelated and it's smoother. I'm also just going to put some transparency on it that allows me to play with layers at various stages. I apply that, and now we can see the landform pop out. Now this is flat alluvial terraces, and we can overlay the geological maps, and we can ask the geological map what the unit is, and we can see we're in alluvium and we're in Pleistocene age, 70 to 130,000 year old older alluvial terraces. If we did the same with the lighter yellow or pale colour, we'd see it's Holocene. So we've got a boundary between Pleistocene and Holocene materials there. Obviously the settlement implications between the 2 layers are quite significant. The other thing we can do here is we can quickly put some contours on this. So I'm going in with my selected elevation model. I'm going to tell it I want 1 meter contours. Normally I'd tell it where I'd save it so it's there for next time. And I can push run, and we can wait not too long. Now we've got contours. I'm just going to quickly change the color of those contours because you won't see them very well like that. And that's just accentuated the boundary there. So we can zoom in. We could do a tighter contour spacing which show it, but we can see the boundary of the terrace, or that particular spot might have some fill. We can see the boundary of some terraces around, and we can check the mapping of those terraces and see where they are for a particular project. So really good first use. Second place we're going to go now is we're going to go over to Omapiri on the Hokianga Harbour, and hopefully that's coming through at a reasonable time. Sally, let me know if things are lagging too much. It's coming through pretty good, thank you. So what we have here is, again, we have the LiDAR digital elevation model, and I've put some contours on that. What I have for this site is I've got a little bit more data. So for this particular site, NZTA had some photogrammetry done as part of some work on the highway that's affected by some instability. So for this particular site, we not only have the digital elevation model, but we also what's have called the digital surface model from the photogrammetry. The digital surface model, being from the photos, isn't penetrating the vegetation and hasn't been processed to take out structures. It's staying the top of the canopy there. So what we can do as an example is we can draw a cross section through the site. So I'm going to add the digital surface model, and I'm going to add the DEM, which has come from the LiDAR. I'm just going to change the color of the LiDAR so you can see what it is there. And now I can draw us a cross section from a beach partway up this slope. And that's now loaded up there for us. And we can export those points and create cross sections for that. as I move across, if you look on the top, you'll see a little red dot moving across where we are, but we can see we're down on the beach and they're matching approximately. We get up on a vegetated slope. Another thing I can do here is I can turn on an aerial. So we can see we're coming up with this vegetation and the DSM's picking up top of the vegetation, but the LiDAR's picking the ground underneath. We come where there's a bit of grass and they're both matching, back to some vegetation. We've got the road and the roadside drain and some vegetation again. So quickly showing the difference between those two models. And as you can see at the top there, we can shade and we can overlay various bits of layers and play with that slope to look at it. And I'm not going to dwell too much on this particular site, but it is affected by some fairly large scale instability that moves every couple of years across this whole slope. Now we're going to move to our first tryout with our red blue glasses. So hopefully a good number of you have managed to get hold of some red blue glasses. And if you put them on now, hopefully you are seeing this image in 3D. Now I'll quickly show you what I have done to do that. So all I have done is I've gone and downloaded the images from RetroLens. I've actually cropped them so that they're showing the same extent. You've got to have sequential pairs in a flight run, so they don't completely overlap. So I'm just selecting the two of them and I'm just bringing them in to the program. Normally they would come in on a side-by-side view, but I've already turned on the anaglyph function. This little button here puts them as a anaglyph, as we're seeing here. And I've got another little button there that can help with some alignment. They don't always line up exactly. And then I can use my arrow keys as well, just to adjust the alignment as we needed. And that's brought us in, and that's as simple as that to be viewing it in 3D. With this image, we can see a moderate amount of features here, but we can also zoom in and see features here. Now I've picked this particular image as one that comes up particularly well on our screen. So hopefully we can see a number of ridge lines and features well defined here, but we can start picking out shallow slip features. I think this is a 1960s aerial photo, and we can see the sort of gully head and shallow erosion features. We can also move up to Ding Bay. Now Ding Bay, if anyone knows it, it's a nice spot. Kids have enjoyed playing in a rock pool following an octopus around here over summer. But here we're in Greywacke, and then if you look at the rock, you'll see it's very different here. So halfway along the beach, we're changing from Greywacke into Whangarei limestone. And the photo's sufficiently good, we can see the blocky nature of the limestone. We can also see some shallow slip features along this slope around here, and the general shape of this landform really well. We can come across and we can see some gullies that are looking pretty hummocky and a little bit of a concern for development if we were to look at it. But we can also come through the north where we get some other features where we're getting some more extensive signs of instability with our arcuate shapes and our hummocky terrain. And really quickly we can start identifying between more stable ridgeline features or more stable terrain and more unstable terrain. We can do a similar thing in QGIS if we go to that. So we'll take our glasses off and I will come to Lang's Beach. So this is a similar extent of the LiDAR terrain model. And again, we can zoom in, and if I manage to find the spot, I do have imported the old aerial photo into this as well, which is relatively straightforward to do. And we can see we have a bit of an instability feature here. We can see in the old aerial photo. We can have a look and see how well that shows up with the LiDAR, with the contours over it. And we can see definitely see the feature in there. Definitely shows up really nicely in the old aerial photos though, but we can work together to understand both of them. We can move back up in the Ding Bay around where the coast with the boundaries, and we can look at a geological map, and we can see the Greywacke mapped, and we can see the Whangarei limestone mapped, and we can also see over to the left here, this light orange is the Rurangi Formation. That's the northern part of the Waitemata group. So we've got the Waipapa terrain, we've got the Tikawiti group and the Waitemata group here. when we start looking at this beach, this area, we can see a larger scale area here that has some signs that it's got some elements of risk, but we see some more defined slip feature up in here. Along the coast, we see all quite well defined, these slip features along the coast. And then we can zoom out and we can move up to where we saw the less stable terrain earlier. So again, I can turn the aerial on, and we're just off the aerial actually. We can see this more unstable features here again. Again, seeing both ways complements it and helps us to see them really well. Now moving on to our next site, we're now moving to Mahuta, which is south of Dargaville on the west coast. So this is again our elevation model, and I'm just going to turn on an aerial image so you can see. Hopefully the aerial image is all right. Loading, Sally, if it's coming through. Very good. My internet's obviously working better than it was the other day when we did our trial run. We can see we've got a grassed area. This is all underlain by sand, and we've got the west coast and the big waves bashing in. So one of the great things is LiDAR and aerial photos are all a snapshot in time, and being able to compare them, we can see how the landscape's changed over time. Being on a west coast beach, we might be worried about coastal erosion or how fast various things are happening. If we look at our DEM, we can see some gully features up here. This area actually has a cemented pan through it that forms this quite defined crest of this slope. In this slope, we can do our cross section again, and we can see at the sort of plateau area, we can see a vertical or subvertical top to the slope, and then we see this slope here, which from the aerial photos we can see is quite vegetated, and then we can see some deposits at the bottom of the slope and our beachfront, and obviously once we get to the water, the LiDAR bounces off the surface and doesn't penetrate water. But we might want to understand how active this landscape is and what changes have occurred. So one of the things we can look at is if we look at, say, this little mound here, and we can see the shape of the edge of this plateau area here, and we can now come back and look in our 1950s aerial photos. And we can see it again, and we can see back then the landform wasn't particularly stabilised with vegetation with lots of sand, but we can actually see, zoom in, we can see that little mound again, and we can see this little scallop we saw before and this larger one here. Likewise, we can also see this gully that's eroded into the landform up here and some of the area there. And we can compare these aerial photos. I was using this little mound because it's a distance I can measure or use as an indicator, and it shows this landform hasn't changed very much over the time. So even though we're on the west coast, not much coastal erosion has occurred in the period between, I think, 60s is this photo, or 40s, 50s maybe, and the present day. And we can step through the various areas of photos to look at that as well. If we go back to our QGIS, we can see the back of the beach is at an elevation of about 5 meters, 4 or 5 meters. So assumably most of the wave energy is dissipating on the beach itself rather than running up and eroding the coastline. We can see where we've got these features eroded into landscape. We've got deposits on the beach which are not being eroded away. They've formed fans and more recent dunes along the coast. So we can start understanding how this landscape's changed and how stable it is, and quite a bit about it, the morphology of it, and beyond that I'll leave you to seek more from a coastal expert rather than myself. Our next site we're going to is back in Whangarei, and we're sticking with QGIS at the start of this one. So this is the tile I've pulled out to look at it and our contours and the area. If anyone who wants to get their bearings, the warehouse is up over here. This is the Seminoff Stadium, a cricket ground. The new opening bridge is across to the side here. We can zoom in, and the feature I was wanting to look at was this feature around here. And we can see a bit of a break in the slope, a bit of an arcuate shape, and you might wonder why we've got a railway corridor with a nice linear shape here and suddenly bulging out and becoming a little less regular here. So to try and understand this feature, we can again go back and look in the old aerial photos. and pull it up here. So this is our aerial photo, and we can see the wider area of Whangarei. We can see, if I zoom slightly further up, we can see the town basin in Whangarei of what it used to be. We can see where you're shopping on Pack and Save used to be under the lighter basin. And we can see large areas of Whangarei that have been reclaimed that were mudflats back in the day. Apologies for that. And we can zoom into the particular area we are looking at, which is this zone around here. This is, we can see, I believe, a scarp coming along here with an area of maybe some grabens and some breaking up of the slope and around. We can see what looks like a relatively fresh face on here, assumably a cut batter. If you look in the book of the Geology of the Whangarei urban area, it talks about a landslide being triggered by the railway cutting in this area. I'm not sure if they had direct knowledge or they just did their background and looked at the aerial photos and inferred from this. But we can clearly see the scarp in this, and we can see how this is bulged and changed out, like we saw in the LiDAR data. And obviously engineering around this area, if anyone came to you and said there's a nice block of undeveloped land we want to do, you can clearly see there's some severe issues to watch. Well, we stay with the aerial photos, and they're going to jump us up to Kamo. So now this is looking at Kamo in, I believe it's the 1940s. Sorry, I haven't got my years written down for me to reference. Kamo is underlain by coal measures, and there's quite extensive coal mining under Kamo. And I'm going to zoom in now and look at where Kamo High School is. And what we can see in Kamo High School is we can clearly see some sinkholes in the field here. What we can also see is another sinkhole here, which may actually have been a ventilation shaft or might be a sinkhole. We can see another sinkhole up in the paddock here, which is now buried in the middle of a road. We can actually see the old mine entrances where the tunnels used to go in, and there's more that were formed later on. Looking at what these sinkholes are, where they are, we can head back to QGIS. And we can load our aerial photos in, and I've georeferenced it. You can see matching with the streets and other things not too badly, and we can see the location of these sinkholes. We can pretty quickly map out some sinkholes, and there's another depression shape feature here. I'm not sure if it was just some vegetation changes or something else here. And we can turn our old aerial photos off, and we can look at where that sits relative to the modern day Kamo High School. No one's built a building over it just yet. And I understand they're not going to when they do the redevelopment. They're in the planning stages for. We can also, the mines are reasonably well mapped in hazards on the Whangarei District Council website, but we can go back to some of the original mine plans and look at where those sinkholes are. So this is overlaying these sinkholes with the mine plans we can get. And we can see the area where these sinkholes are on the edge of a mined out area. And I understand this area was pillared, so they let it collapse in behind them as they came out of the mines. We can look at what other ones have we got there? We can look at Keir's paper. He put some maps together of the minefields back in the 50s and did a paper on the geology of it. The hash there means it's pillared, and we can see his old boreholes back from the 1920s through to the 50s. We can still find the records for those old boreholes. We can also see some faults that Keir's mapped, and I confirm these faults are definitely here. Not only did it mean the coal stopped and they had to go put more tunnels to get deeper, we're looking at a bridge abutment for a shed path there, and the rock level drops about 8 meters between our borehole and our CPT, which are a whole 3 meters apart. And finally, if I remember where I've put it, forgotten where I've put it. I had also the 1920s up the top here. We can also look at our 1920s geological map with a modern overlay, which is of mostly interest, but also gives us some idea of where the older coal mines in the earlier stages were. One final last comment in this area back on our aerial photo. Anyone who knows this area, the Carmo bypass now comes up the valley up through here. When they're building the Carmo bypass, they had a significant problem on one of their cut batters. They called it the cheese cut batter, I believe, where they thought they're going to be in volcanics, and they discovered some alloxin that actually occurred in this area here. And if we look at this aerial photo, we can see from a relatively regular uniform shaped landform here, there's some slight shading and some slight hummocky nature to the slope here, so we can see the faint outlines of the issues they had with a bit of warning. Obviously it's much easier for us to see it now. We can zoom in and look rather than dealing on had to printed out copies of aerial photos back in the day. So that is Carmo. Moving back to QGIS and moving not too far from Carmo, we're now heading back to Kensington Heights, which is a reasonably recent subdivision. Sorry, the wrong layers. Yeah, it's been developed over recent times. Looking at the landscape here, we can see the various cut platforms formed for houses and development. One of the notable bits in this landscape is there's an area at the top here that's more hummocky and irregular. If we look at our geological maps, we can actually see there's a little bit of alloxin sticking on the side of our Greywacke Hills here. It explains the hummocks. What we also have in this particular location along our Greywacke ridgelines and things is a lower change and a more lower terrace level here. So it's a change in the shape of the landform, which indicates there could be a change in the geology happening underneath. If you walk up this creek, which I've done, up here you'll find some nice Greywacke outcrops. But if you walk further down the creek, and here you'll actually find evidence that this might be a block of the Carmo coal measure unit. So a little block of different geology that's not mapped. The coal measures being bedded and with defects and other things standing at a lower angle and explaining why we've got the change in the landform. The other useful thing from this site is we have both LiDAR from 2009 and 2018. So fairly simply we can use our process to here. We just go raster calculator and we literally add our two layers and put a minus sign between them, and we take one off the other. And from that we can get the difference between the two of them. So I've done that, and now what we're seeing is an elevation model that is the difference between 2009 and 2018. So not showing the landform, but changes in the landform over time. There's going to be a bit of error between the two of them. There's going to be some differences where they've processed the LiDAR for the vegetation and the structures, but it gives us a pretty good idea of the cut fill, particularly where there's been significant development of house sites and some filling, some cut and filling up the roadway. And for example, on this lot up here where there used to be an orchid house here, but there's known to be a bit of fill, we can see that that fill is sort of only up to 1.5 meters deep here. So giving us a good idea and changes of the landscape where we have LiDAR coverage at both ends. And quickly looking at the same on another site, this is a valley floor out in Tutukaka where we have some historic filling done and some more recent filling done. It's underlain by some soft soils for development. So it's a quick way of checking. Most of the fill was said to have been done pre-2007 with it on here, and we can see that it here. So what we're seeing is the amount of fill that's happened over these lots here is up to sort of 700 mil in recent years. So it's good to know that the 3 meters of fill beneath it is old. Also, we can see that there used to be stockpiles sitting at the time the LiDAR was run over much of the site. So it's showing as a depression on this because the stockpile's been taken away with respect to the current landform. So that's an introduction into using difference between LiDAR. Our next site, we are heading up to Russell. So this is Long Beach in Russell, and recently I was up on a site, and while I was on site, I looked and there was a small outcrop of Greywacke. and in the outcrop, when I looked at it to my eye, there was 2 main defects there. You can see this fracture here following this defect, which is mostly heading into the page, and then we can see a defect that's sort of parallel with the face the photo's taken coming across the page. Now this photo is taken at the base of this slope down in here. Now it was relatively apparent sitting there with my printed LiDAR model on site and looking at that the defects we were observing in that outcrop matched this alignment of this ridge line for one of them here, forming this face here. And the other defect set, which was sort of orthogonal, was cutting back on this angle here and controlling the formation of this slope here. So from looking at the small scale observations in the rock on site and looking at the terrain, we could match the 2 of them together and help understand the landform. This is obviously a coastal area, been subject to historic coastal regression. So an oversteepened slope along here, and we can see the various defects and landslide features that have developed accordingly. Won't dwell on it too much more, but I do have it here as an aerial photo we can look at quickly as well. So that, if you want to see it in 3D, is the same landform. LiDAR shows it pretty well, although, you know, for example, a feature in here, we can see it's got active movement at the time and looks like possibly some flow coming down the gully, and it helps us understand some of the activity and how it's changed over time as well. And we can fairly well see some other features on some of these other ridge lines and start mapping and understanding those pretty quickly as well. So moving away from there, sorry, we're staying with the aerial photos. Now you might have taken your glasses off. We're now moving to Abbey Caves Road. People who know Whangarei might get a hunch for what we're looking at here. But if you look at the photo, particularly in this sort of area in here, and see if you can see anything that might be unusual. I'll just zoom in a bit more for you. So I'm not sure if you can see or picked up on it or not, but we're seeing some depressions in the landscape here. So instead of seeing normal valley formations, some here, maybe some over here and around. So this is an area that is underlain by the Whangarei limestone, which forms karst formation. So we're starting to see some sinkholes. So we can go back to our LiDAR. And this is what this is looking like in our terrain model. So if we zoom into the area we're looking at, and we can see these sinkholes showing up as depressions really well in the LiDAR. And it's also penetrated through the vegetation. And we can also start seeing how the sinkholes are occurring on linear alignments where they're above an underwater stream through the limestone. I believe, if I just put on an aerial photo, turn this off for a moment, I believe the Abbey Caves that you can walk down to and actually go caving in are in this bit of bush here. So if we look at those, we can see some sinkholes. I'm not sure, maybe that one you can go in a cave that way, I think, and some down here you can come back in a cave back this way, I believe. So again, the LiDAR is doing a pretty good job of helping us understand that karst terrain. Next one, we're starting off with our aerial photos again, and starting looking at the wider scale of the landscape. So this is in Whakapara. I guess it's maybe 10 kilometres north of Whangarei. And the terrain feature we're interested in is this in the middle here, which I will zoom in. And so what we're wanting to do is understand how this landform might have come about. It's a bit of an ugly, funny landform. We've got lots of odd-shaped slopes, various drainage patterns. Within the middle of it, we've got a nice, rounded, smoothed area with a little pond sitting in it. So quite a unique form of landscape, I think. And what we can do is we can now come out of this and go back to QGIS. So I've loaded in an aerial photo and referenced that. So we're seeing a similar view to what we saw now with our uniform shape and our funny shapes all around it. And we can put on our geological overlay. And we can see that this red in the middle is volcanic, so we're actually looking at a little volcano. The whiter colour material around it is melange of the Northern Lachlan, so pretty weak parts of the Northern Lachlan, pretty sheared and pretty jumbled up. And the geologists, when they put the map together, have gone to the effort of mapping some as not just melange, they've mapped these as landslides within the Lachlan. The white around the boundaries is the Hikudangi swamp alluvium. So we can see we've got a volcano that's come up through the Lachlan, and it has formed a volcanic feature over the Lachlan, but the Lachlan has not been strong enough to support that feature. And the Lachlan has slid away from this feature here and resulted in the landscape we see today. So I will turn off the photo and turn on our terrain model, turn off our geology, and we can zoom in and we can start to see some larger scale instability features in the terrain like they had mapped on the geological map. We see what I'm assuming is the crater with a little pond still in it and a drain out from it. And we can come and look on some of these slopes. I understand there's actually some rock faces here with rocks sort of toppled out and rundled down, but I've never had the chance to get up and see it. And we can see some more uniform shaped ridgelines where we might be more comfortable on. And we can see some pretty jumbled, muddled areas that we'd probably want to do a pretty good investigation in on this terrain. So we can start working our way through this terrain and hopefully identifying better spots for development and more troublesome spots to be involved in. Our next spot is heading to the south of Whangarei and looking at an aerial photo. So I've just got it part screen so we can see in the centre of the area we wanted to look at. So we're looking at this part of our map here. So what we're seeing is a bit of a spur ridgeline coming out, and another little funny ridgeline feature down here, and our drainage features coming down. So looking at this photo, we can obviously an instability feature in here, but what we're really wanting to do is step back and look at this wider feature and thinking about what the terrain means in this area. So what's immediately apparent is it's not nice and uniform. It's not a nice smooth slope up to a nice curve over on a nice ridgeline crest and down the other side. We've got variable shape sort of benches and arcuate features. We've got blocks that stand out more proud. We've got steeper slopes. We've got shallow slopes. It's not a very uniform terrain, which gives us some hints that there's some defects and some nasty stuff lurking under the ground if we want to get involved in engineering on this site. Anyone knows the North Power Depot in Whangarei? It's actually on here and is on a landslide itself. So going back into QGIS, sorry, taking my photos off, not my headphones. We can do it, so that's the wider area. We can see where North Power's got their buildings in that feature, but we were looking at the central part here. So we can start seeing that same landscape, but in a bit more detail. We can see some benches and some steeper slopes. We can see a block of material standing steeper here, which in the Lachlan indicates you've probably got a block of stronger material, but it can change pretty quickly. We can see some sort of arcuate shape features here, and we can start seeing some linear alignments through some of the geology here, start giving us some hints that might start helping us unpick this landscape if we were to look at working in it. That one. So moving now out to the Whangarei Heads, out to Ruatahi Bay. So this is a picture of Mount Aubrey. Everyone knows Whangarei Heads. This is Ruatahi. Mount Manaia is just off the side to the right here. This is geological maps popping up. So it was a old stratovolcano, erupted maybe in the late stages of the Lachlan emplacement or after the Lachlan was in place. So it's come up and intruded through the Lachlan, overlying the Lachlan, and then it's been massively eroded back to the various pinnacles and other volcanic features we see on the Whangarei Heads. So we see our volcanic formations, we see our Northern Lachlan Melange, and we see our landslides map features that are in Northern Lachlan Melange as well. But what we have is a volcanic landform over Northern Lachlan again. Set off our geological maps. So in the terrain model, we have pillars and bluffs and things up here, so we can start seeing terrain features where rocks might roll if they ever to fall down and roll off. Of note, later on we can look at an aerial photo and we'll see there's a rock in this gap here. It's not here on this model, it's actually sitting there. So that rock rolled down and stopped in 2011 during Cyclone Wilma. The property owners here heard a pretty loud noise rolling through the middle of the night, and when they went out in their houses in the morning, they had a new garden feature sitting up slope. Thankfully it stopped before their houses. We can also see some more uniform regular shape features, but with some arcuate shape features coming back up, which we'll look again in the aerial photos. We can see this feature here. Just going to pop on some more aerials contours. Here looks a bit of a fan shape feature with some modification to me. I'm not quite sure how it might have formed, whether it's a volcanic landform or maybe once upon a time it was a big collapse and we had a big debris run out that formed a fan down here. One to ponder on. To the side, we start seeing a more defined ridgeline and some features here we'll come back and look at. But likewise, we can identify this nice flatter plateau area here where engineering should be relatively straightforward. So moving out of the terrain model to our aerials. Actually, sorry, I think that might go one before that first. So here's our older ones back in the 1940s. It's a thin slither again because we're limited to what overlap on two adjacent photos will give us. First things I notice really apparent in this is this area up to the north here, where we've got some quite well-defined landslide terrain features in and around another smaller area here. One hopes the new house being built in there that just pops over the slope took into account what we see on these photos. We get some quite significant shading from just the elevation on these mountain features, and the photos offset and skew on them, so they come a bit blurry and funny on your eyes. Hopefully they're handling it all right. But again, we see these rock fields quite well, and we can see, for example, this area here, which is displayed as a nice uniform slope with some arcuate features in the terrain. We can see the shape of these slopes on this, and we see some little regression features up in here. Yeah, nice uniform landform over here again, and we see a more jumbled bit in the zone in the middle, and start getting a reasonably good understanding, insight into this area. Likewise, we can come up to the north, and if you look at the geology and read a bit, you'll find that there's a exposure of the Tikawiti group that's been pulled up into the Lachlan, twisted on its side. So we have, and I forget which way around they are, there's a block, I think this is the limestone and this is the sandstone, but I could have it around the wrong way, sitting in the foreshore, and we can see that from the coloration in the aerial photos there as well. So that's the earlier photo of the area. We can come to a later photo of the area. We've got a bit more coverage, it's taken from a bit higher. Again, we can see these landslide features up to the side here. We can see the general shape of the terrain. We can't zoom in as far because they're higher up and not as well the resolution. It's pretty hard to see. I'm just going to adjust this photo for the highest up, but I think it's maybe that rock here, or one of these rocks up here was, oh no, it's that rock where the hand is there that rolled down in 2011. So again, getting some pretty good insights from the terrain in this area. Staying with the aerial photos, we're just going to jump across to McGregor's Bay, which isn't too far away either. So we were just off to the left of the screen before, and we're going to look at this feature in the middle of the site here. These are all areas that are, this area is all mapped as high stability hazard by Whangarei District Council. when you start looking at the aerial photos, you can start to understand why. Although one of the challenges you do start getting on some of these slopes is they're starting to get sufficiently flat that the terrain features are harder to see in the aerial photos because there's not the vertical contrast. But we can see in this photo some hummocky features in the middle of our photo. We can see the road formation. You can see there's a bit of a ridge line coming down here and a bit of a ridge line around here. And we can start getting some understanding of what the features were like. One of the great things about the earlier aerial photos, this is 1942, is we're looking at sort of maximum land clearance in Northland, but with relatively limited landscape modification. So we can see what the landscape was like in many places. But jumping back to QGIS again and jumping over to this area. Again, we can have a quick look with our geological maps. And we can see there's a large area here that is mapped as Holocene landslide deposits, which is never a very good start. We've got a little offshore island, which is a little volcanic feature. Zooming in a wider sense, we see we've got a ridge line coming up this side. We've got another ridge line coming down this side. In fact, this photo here is off to the side of the ridgeline to the right on that photo. And we can see the ridgeline is actually, I believe, made up of Mahurangi limestone, which is the stronger part of the O'Loughlin. We're just getting off the ridge on this photo, and we see we've got a swirl of the limestone, and then we've got the grey mudstone here. So it's an indication of what the geology is like when we're looking at these photos. This is the road. We see there's a drop in the road, more apparent on site. We can look soon where that drop is. Likewise, we've got a crack and some offsets in the curb in our footpath. That's what the Mahurangi limestone is in one of the outcrops I'll show you shortly. And finally, this is if you go and drill some boreholes, what your geology will start looking like to explain these landforms. So we come back to our terrain model. So what we're seeing is this ridgeline along the side here. We've got the Mahurangi limestone outcropping in the cliffs. So we're inferring this has been formed by a block of limestone within the O'Loughlin. The reason this ridgeline is pretty irregular in shape probably is because it's been swirled and muddied, and the edges are not, a regular shape. They're a very irregular block. If you actually go down the foreshore, you can see there's some volcanics here and an interface to some mudstone and limestone. With the terrain, we can actually zoom in reasonably well on some of these features. I can put more contours on to accentuate some of the features. The drop in the road, the first one I showed you, actually comes across the road here and around here, lining up with these terrain features quite well. Likewise, the offset in the footpath was happening here, again, lined up with these terrain features here. We can look at our aerial photo, and these are the areas of most significant hummocking from back in the day. Seeing them but not seeing them as defined in the contours. And we can start seeing, for example, on the slope to the right here, that was relatively uniform looking in the aerial photos. We can actually start seeing some of the finer hummocks on it. We can see a little scallop above the road here, and we can see a bit of a heave coming through this area here. We can see various features and benches and start unpicking the terrain on the slope, which obviously to understand you need to quite a good investigation to understand it. Finally, on to our last stop on the tour for today. We are heading off to Onerahi. So this is Onerahi. I'll just turn off the contours, start off with our geology. So Onerahi, most of it's a bit of an irregular shaped plateau, really flat on top with slopes all around the sides. So what's happened here is we've got a volcanic flow that's come down. It's quite old and it's quite weathered, but it's formed a more erosion resistance landform. So the land around it has eroded more quickly, hence we're left with a plateau where the volcanics are and exposed geology all around the side of it. It's come over some more unstable units, so we have stability issues around the slopes in Onerahi. First thing we can look at is another yellow area, mapped landslide, so we can have a quick look at this feature. So I'll turn off our geology. turn on some contours, and we can come up and look at this feature here, and we can see a fairly large scale feature in the landform. We can see that part of it's been developed. I'm not aware of any problems on any particular houses there, but it is in an area where you'd want to apply a bit of caution. One of the things I do note in this area, if you drive up this road at the moment, is there is a bit of creep and dropping out of the road, slumping over time somewhere in here. I don't know the exact location. One of the things we can do is we can go back again and look at our old aerial photos. So again, we've got a bit of a narrow strip just because that's where our image overlaps allow, but we can go up and we can zoom up to the top. And we can see in this larger scale terrain feature, this is old Onerahi Road, the new road's coming up somewhere up through here. And I think the instability is probably occurring somewhere in this zone. So we can see these sort of benches and terraces that I haven't been out and mapped to know for sure, but it's quite possible that some of that instability that's occurring now may align with some of these features, and these probably explain why it's occurring. And I think we'll leave the aerial photo. We'll drop back to, I'll move on to a later aerial photo, but one that lets us see a bit more together. Zooming in at the top up here, we've got a bit of just a random mound. We can actually see an old power site on it. To the north side of this, we again see a bit of shading and hummocky areas that we may want to apply some caution on. We also see some more uniform slopes on part of it as well. But the main area of interest around Onerahi is the edge of the plateau. And we start looking, we can see a bit of an arcuate shape feature around here, and we can see some more hummocky areas in it, an area that's likely been subject to historic instability. And we can work our way around the plateau and see some other features of various scales and at various stages of development, and start unpicking some of these features as well. And we can go back into QGIS and start looking at some of them in QGIS as well. This is the first bit we looked at where the old power was. We can see the formation of the road up through it now. You can see some features around the slopes, but not particularly well defined on this unit of it. We can come back to the landform around here, and we can look at a relic feature around here. We can see it's been developed for houses by now, but we can still see some irregularity in the terrain. And we can work our way around the edges of the site, picking up on some of these features. Just going to pop up to a valley at the north. So we can also see some irregular shape features in this area. But moving into this area, we can pick up that our east-facing slopes are flatter than our west-facing slopes, so likely some controls on the geology there. We can pick up some shallow landslide features on here. But on the other side of the valley, we can pick up some minor ridge lines coming down that are indicating there was a little bit better stability in some of these zones around here. And also off the side here, we come across and we've seen some alluvial deposits with some fan features and some terraces and some lower lying areas. And again, our grey-worky terrain where we can pick up on our features. One final point on these is if you are using the online maps from GNS, it's really quick, useful, nice to see them over the terrain models, and we can jump in and we can see our geological units. One thing to be careful of is this is mapped as Ruatangata sandstone. You can get two types of Ruatangata sandstone around in these maps. One is Ruatangata sandstone in the Northland Lachlan, as we have here. So this has been pulled up and incorporated into the Lachlan. So it's got a variable amount of breaking up in the Lachlan. It's quite different to autochthonous Ruatangata sandstone, where it's not in the Lachlan, it's in situ. And the whangaro, the geology of the whangaro urban area, actually calls this something else. It calls this Oamahuta sandstone. And if you read the TNT hazard studies of the area, it is pretty pessimistic on the performance of the Oamahuta sandstone. So that is the end of the tour and the presentation today. So I hope you have found that worthwhile. If I manage, I'll quickly. All right. Move. So finally, some pictures off. Some, I think, artistic insights into the geology in the O'Loughlin. Sometimes it's pretty fun pulling out bits and looking at them. But time for some questions, and also a recommendation to make sure you've read Bruce Hayward's book if you're working in Auckland and Northland and need some brushing up on your geology. You'll benefit significantly from it. So thank you for listening.
Thank you very much, David. That's awesome. I learnt lots and thoroughly enjoyed playing around with stereo air photos, as always. We've had a few questions come in. If anyone's got any other questions, please just pop them in the Q&A box and I'll read them out to David. The first one's just a comment from Andrew Hurley. Nice use of DSM versus DEM. Note that Lynn's data service also has DSM available. You may have known that, I don't know.
Yeah, it probably is. I haven't pulled them out and I don't use the DSM too often, but it was just one site where I had them together. Yeah,
no, it certainly looked quite cool on the ability to create those cross sections is fantastic. Anthony's asking what software is being used to 3D visualize the air photos.
So the software is Stereo Photo Viewer. It is a random bit of freeware that someone pointed me in the direction to at the GIS course, so you can just go online and download it. It is, I'm sure a link can be sent out afterwards so people can find it.
Yeah, no, that's cool. Maybe just add when this presentation goes out, maybe just add a slide or something that has got a couple of links on it or something.
It is. There was a link in the presentation at the start. Yep.
That's fine. Another question. Back in the early to mid 2000s, TNT did a land stability hazard analysis of the whole Whangarei 8 DC area using stereo pairs, geological maps, DM, slope for the council. Do you know the work and how does this stand up against the new DEMs and the on-screen 3D programs?
So the early mid 2000s stuff was pre-LiDAR, and they actually flew stereo photo aerial pairs, stereo photos or aerial photos for that specifically. In fact, it was prior to there being a good geological map of the Whangarei heads, so they did a map themselves for that. So it stands up really well. They had really good aerial photo stereo pairs and they mapped it really, really well. Tonkin and Taylor have gone back, and the mapping back in the 2000s was only of selected more high development areas. They've remapped the whole council district now using a combination of aerial photos and the up-to-date LiDAR. It's with council but hasn't been publicly released yet, but is waiting on their GIS people who update their websites just to load it up. So it's it's good.
Fantastic.
But yeah, it stands up really well is the answer.
Cool. No, that's really good. We haven't got any more questions. A few comments from people. I've had a few texts as well, people loving it, thinking it was great. I think if you're still in level 4, I'd certainly be taking the opportunity to teach myself and play around with it a little bit more. Those of us back in level 3 are off out to go and do some test bits now. But hey, no, that was awesome. Oh, actually, hang on, suddenly had a flurry. Where do you get the geological overlay?
So GNS has the data source there, so you just basically find the web address and add a web address into QGIS and it pops up. So it's there and you can get it.
Cool. Someone's just asking what the GIS course you did was. It was Colin Masengard from Australia, wasn't it? He came over in 2019.
Yeah, yep.
My understanding. And so just we were trying to get him back over this year, but we can't do it until A, the borders are all open, and B, he's allowed over here. So as soon as we can get him back over, we'll run the course again. My understanding from feedback from people who were at the course is that it's better run in person so that he can actually help you with, if everyone's got their own laptop and you've all got software running, it makes it a bit easier.
Plenty of YouTube videos around as well. You can hunt your way through and things if you start.
Okay,
and
cool.
When you add the DEMs off the file, they just drop in georeference, as long as the main thing is when you open the program up, select your coordinate system so you're not working in some random system from the other side of the world that's got a skew projection in New Zealand. Choose a New Zealand one so it's got your right projections and your distances work properly.
Yeah, fair enough. Can generated cross sections be imported to slope stability software or other softwares?
Yeah, so when you do your cross section, you can output them as a table of points or as a picture. So yes, you can either export it as a picture and draw off if you're low tech, or you can export it as points and import as just a table. So yeah, pretty quick and easy.
Brilliant. How often does this type of terrain analysis trick you into identifying features that aren't there?
Obviously, you use it in conjunction with going and looking over the sites and your investigations, and you add it as layers of information together. Not very often. I'd say you're more likely to miss features and regret not seeing them later on. And you ignore features that you see in aerial photos and in LiDAR terrain models at your peril, really, is more what I'd say.
Yeah, I'd say probably a very good starter in desk study, and then go out and truth check it out on site and see if the features are visible, and if not, why not? You know, has the site been redeveloped, or is it just masked by a few trees or vegetation or what have you?
Putting them all together, it's obviously most powerful when you've got the site investigation, your site observations, the aerials, and even your Google Earth and other things to put together.
Yeah, totally. Anthony asks, do you find the stereo photo viewer more powerful than just draping air photos on DM and QGIS?
Yes, and I guess one of the things is for many sites, the LiDAR is showing you the most features and getting the best value, but there's quite a few where you get a bit more out of the aerial photos as well, just depending on what features you see and what you're looking at. When you're actually doing the aerial photos, you're putting two photos together, so you see a little bit more just for the fact you've got the information from two photos than one photo. And if you're draping the old photo over a modern elevation, you've got potential that there's a bit of difference in your georeferencing, and you've got potential there's been some changes in the meantime that sort of distort the old photo. So it can be nice to drape the old image over the modern terrain, but there are some downsides of that as well.
Sure. And one last one, is it possible to import the stereoscopic photos into QGIS so direct comparisons can be made between retrolens photos from different times? That's what you're doing, isn't it?
So you could import the stereo, so you can save the images as a stereo photo, and then you could import the stereo photo, so you're looking at the stereo photo in QGIS itself. You could do that. As to how much it would distort or change location, I'm not sure. You can get in professional GIS, I think ArcGIS, there's a module you can add in where you can have the stereo photo viewer at the base of it, and you can trace over that, and it traces onto your GIS model. So there is a professional model around for doing that sort of stuff. You just have to play with and see. I've never tried.
Okay, fantastic. Someone's just asking you where you access the stereo photos from. That's retrolens, isn't it?
The photos are just all downloaded from retrolens. Yep.
Yeah. Cool.
Sometimes it takes a bit to figure out which photos and which directions and how to go about it. You just got to persist and find your site and work through, and sometimes it's easy, and sometimes you start with Google and work back through the years to find them.
Yeah, sure. Another question here is there a database of landslides or instabilities for overlays? You talk on this one first, and I'll add on a bit if you miss it.
There's a bit of an ad hoc old database from GNS that you can find on their website. There is, if you're in Whangarei, you've got the hazard mapping for Whangarei, which is a pretty good indication, although you've got to do a bit of interpretation as to whether you're looking at a unstable allochthonous slope or some shallow slips on Greywacke. But no, there's not good databases that you can use reliably. You need to do the basic geomorphic assessment yourself if you're going to have any confidence.
There is, however, one being development, and it has just been issued, I think, and they're calling for people to add to it. The New Zealand landslide database is calling for people to map landslides that they know of, be that small, big, ongoing, having happened and now finished. The idea being that it'll be similar to the NZGD, that it's a maintained database that anyone can log into, and you can georeference the extent of the landslip, or you can just have a point on a site. There is some seeded data in there, which was taken from the original GNS landslide database, but I think there's a lot of work being done at the moment trying to see that and build that so that it's much more of a useful tool. As with the NZGD, it requires everyone to chip in and log what they know of, I guess, although that would probably take several years up in Northland, I'm guessing.
Yeah, one of the things is, if you look at some of the Chris Massey type stuff, where they're doing landslide prediction and other stuff with GIS, a lot of that's visual mapping of landslides and things, which works really well where you've got fully evacuated areas and they show really well on aerial photos. Where you start getting into soft rock, Lachlan type things where you've just got creeping slopes, you have to look at the shape of the terrain. You just can't see it from bare landslide scarps and things. So that makes it a little bit harder for some of that later stages of things. I have thought it would be fun if someone took the Whangarei District Council hazard mapping and assigned various attributes and tried to machine learn it and forward map the rest of Northland and see if that worked at all. I think it'd be a fun project for someone.
Interesting project.
Yeah.
I always just asked, are the retrolens photos georeferenced, or how do you get it georeferenced?
They're not georeferenced. You have to georeference them yourself. There is a georeferencer tool I can bring up here in QGIS as an add-in, and you'd basically just add a photo. It's one of Onarahi, and you pick a spot that you can see where it is on that, and I'll map from the canvas, and I'll go back to where we were and change some layers so I can see, and that spot I was picking roughly here. So you just work your way through, you see the dot there, and picking various points on your photos and hit go, and it tries to match the two for you. And sometimes it takes a few attempts and other things, but you're never 100% perfect, but you can do it pretty well pretty quickly yourself.
Cool. Can we generate sort of geological map from these data if there are some boreholes data available? Quite sure what you're asking there.
Obviously you can refine the geological maps using the terrain data and things. The QMap series has been done pretty well, and there's a lot of time spent with geologists on aerial photos from those maps. So I would suggest that all the aerial photo data has been incorporated when they've built the geological maps. I would say, obviously they didn't have LiDAR, but so you can always refine the geological maps.
Just a note of caution that the QMap series is 1 to 250,000, which is, a massive scale. So I wouldn't be too worried around that. I wouldn't be following it to the nth degree around the edges between particular boundaries. But you'd want to be truth checking it yourself with whatever testing you've got locally, I guess. I think these questions are going to carry on going, but I am going to call it a day there. If anyone's got, there's a link that's just come up. If anyone's got any more questions, please send them either direct to David or myself, and I'll pass them on to David. We can take it from there. Like I said, we'll try and put another one of those GIS courses on as soon as we can meet again in person. So, but for now, thank you very much indeed. That was an awesome talk. Thanks, David.
All right, see you everyone.